Well, thanks a lot, Gunnar, for this nice laudatio. Thanks for the organizer to organize this whole conference, and obviously to Bruker to sponsoring this prize. It's a big honor. So I'm obviously going to talk about my thesis, and usually if you learn, like, if you go into a course where they tell you how to do a speech, they usually tell you shouldn't do the science well chronologically. You should have a story that, you know, we wanted to do this. This is how we saved the world, but now it works. And I'm going to do a completely different thing now. I'm actually going to tell you, like, why I started working on some things, and some of it was actually pretty chaotic and by accident. And I think that might be more interesting for this one. So I have to explain a few things, but I try to keep it light, and so I won't go into too many details. Well, talking about arbitrary waveform generators in EPR, a little bit before the time of most of us, I would say, probably not all, but EPR spectrometers look more a little bit like this. And actually, there's still a home-built Q-band in Gunnar's lab. I think he was actually one of the first pulse Q-bands where you see that you actually literally have physically distinct channels where you can set the amplitude and the phase by hand while tuning it up. And if you show this to NMR people, they look at you with like eyes that they can't believe it. Like, why? So complicated. Now the whole thing, basically this whole box here, it's just inside here. A little bit of a few filters and whatever on top of here. And this is what in Gunnar's group, Andre and Dahl built the spectrometers roughly 10 years ago now. And it just allowed the whole microwave generation, or basically all the pulsing and the shaping is just done by this box, and it also triggers all the other pieces in the spectrometer. They were not the only ones, so there were some early applications. The Eatons actually also did it for CW EPR here. Gunnar's lab, then Thomas, I think Songi, and probably also missing some. And so Gunnar was not the only one, but what he really pushed basically is that you would also use it in DEAR, that you just have better, you have broader excitations basically. And I would say the first few applications were mostly using sequences that we already had, and we just use broader pulses basically. And what I tried in a little bit to do is, at least in the second part, is kind of actually make new things with the AWG that don't have like a direct analog that we had before. And this was actually also where I did one of my bachelor projects, and I actually ended up on a paper here with Andreen. But I think what's important to highlight here is what I did is basically I watched him measure it, I mean, and then help with the interpretation, I guess. And okay, I did one thing. There was this problem in gadolinium that you have all these connected transitions, and if you have a pump pulse during a coherence, and this pump pulse gets too close to the coherence that you observe, you actually destroy some of the observable magnetization. And what I implement there is kind of that you use second-order perturbation theory to get your Hamiltonian and somehow analyze if you actually understand where this is coming from, and then also optimize basically the setup. But I wanted to highlight a bit actually, because for Gunnar, I would say this basically didn't matter at all that you put me on this paper. But for me, this was a huge thing. And this was my first paper I was ever on. And probably this was one of the reasons why I actually also ended up like for my PhD in EPR. And well, then actually afterwards I went to Janet, mostly doing biology. Some people don't believe me when I tell this, but I mostly did biology in that lab. And what I would like to thank her for is that she actually invited me to go to my first REC conference in Southampton. I think I'm back here somewhere. And this was kind of my first introduction to the community, and I really, really liked it. So the first PhD project I did was just a proposal by Gunnar. So I had not really to do a lot with coming up with the idea. What was it? The main idea was using a chirp echo. So you have two pulses and they have some timings. It's usually written, it's the Berlin-Bodenhausen scheme, but there was actually another guy that came up with it a few years earlier. And basically use chirp pulses over a whole the whole echo or parts of the spectrum, you get an echo here, and then you Fourier transform this echo. And then you get spectral information like in NMR. They have a direct dimension. And Gunnar's idea was that you could actually combine this with LDO-detected NMR. So they used this high turning angle pulses, and they will actually show you how this will look in a spectrum to irradiate forbidden transitions. And the point is, if you have, let's say, a nitroxide spectrum like this, which still has a few distortions from the chirp echo. So this is the chirp echo Fourier transform of the chirp echo. This is not a field sweep. And if you now irradiate just with a long pulse at some point, what you see is something like this. So the irradiation frequency is at this point here. But clearly you can see that there are also holes at another point. And if you do this at another point, well, you still have this kind of central hole, but you also get these other holes. And they basically encode the nuclear frequency. What you do in EDNMR is that you sit just on one frequency and you change the frequency of the pump pulse. So basically, instead of having 3 here, you would have maybe, I don't know, a few hundred, but you would sit on one position and observe it there. But what you can basically see already here is the experimental result. Well, you can actually do it in one shot. So because if you have a broad line and you just irradiate, all the holes are already present. And if you just do a Fourier transform of this echo, you basically get the EDNMR spectrum in one shot. Nitroxide is actually the worst example because you have orientation selection, which is different in EDNMR and in this chirp echo detection. But in general, if you have a slightly broader spectrum, maybe like copper, instead of sweeping the whole burning pulse, what you do is you acquire the chirp echo spectrum, then you do the whole burning, and you just subtract the two. The Fourier transform of the subtraction. And I would also like to highlight here, this worked within, I think, 1 month, actually. And this had very little to do with me. It had to do that the idea was good. That was Gunnar's point. The spectrometer worked and it was already there. And in this point, at this point, Andreen was actually already gone. And Frauke was actually kind of my effective supervisor at this point. And she showed me how to use how to use all the spectrometers, which was really nice. Now, this is just an example spectrum for copper. This is some copper complex that Dani made, but I mean, yeah, he not only did this copper complex, this is just mixing stuff together, but he helped me with basically everything else than the AWG spectrometer, and I would really like to thank him for this in general as well. And what you can see is on top is the EDNMR spectrum. The bottom is the chirp echo detected or cheesy detected NMR. And what you can, okay, you have a central hole in the middle. You have some directly coupled nitrogens here in the complex, and some remote nitrogens that you can also see here. And you might think, yeah, okay, we're getting later why I know that these are the remote nitrogens. But the point here is basically just have better SNR. It's the same thing as in NMR. If you just have the advantage of the Fourier transform detection, basically, because you can detect the whole thing in one go. Then you can then another thing you can do here was that you could do 2D correlations. So instead of only using one whole burning pulse, you could use selective pi pulse prompt. And if you think about the energy level for an electron nuclear spin system like this, how EDNMR works is that you hit these forbidden transitions, basically, and this would move the population from this level up to this level here. And that's why you get a hole on this transition and on this transition, actually. If you first invert one of these two levels, you end up in a situation like this, and you might realize that if you now use a whole burning pulse, it doesn't actually act on the populations there. Of course, this is idealized, but you still see basically less change if you do this. So you get no side holes or just reduced side holes. And then you can do a 2D spectrum like this. So on top is just the 1D spectrum. So this is one whole burning pulse and just the Fourier transform of it. And then okay, the difference to the reference. And now you can sweep a second pulse and just a selective inversion pulse through this line. And you plot the frequency of this on this axis here. And if you do this for the whole range, what you can see is basically a high score spectrum, but it's detected by EDNMR. And that's why, for example, here you might say, okay, how do you really know these are remote nitrogens? But if you see it in the 2D, you can actually just read off the values like in high score, basically. Yeah, and I think this is some kind of, so you can do this high score type correlation also in this cheesy detected NMR. Actually, you don't need the chirp pulse. So this you could actually also do with normal EDNMR, but I think no one has ever done it. But in case you would ever be interested in this, you could make it work. That's pretty lucky. And then the nice thing was there was actually some direct application of this. So Anton Ashuyev in the group of Christoph Kopper at ETH, he was working on this titanium complexes, which does polymerization of ethylene. It's titanium 3. And what they just wanted to see is that to be sure that this is actually the active site of polymerization that happens. So they labeled some of these ligands with carbon-13, and they just had really a lot of trouble detecting this carbon-13. So they kind of maybe saw it in Endor, but they were not quite sure. In high score, also maybe it showed up after like 24 hours, but they were also not convinced. And in this GZ detected NMR, actually, it comes up right away. So in check in black, you can see the GZ spectrum in with the carbon-13 label ligands. Then we took it out again. He did polymerization, and what you expect is that at least some of these ligands would, when the polymer chain grows, then the at least some carbon-13 should then be away from the titanium, and you should see a reduction basically in the peaks due to the carbon-13. And this is exactly what you see here. So the difference that you see here from black to red is before and after polymerization, and in blue is basically highlighted the differences. And this line, so basically this one and this one is the carbon peak. And then there are also their combination peaks if we have carbon and nitrogen. This is quite well understood. And we could also kind of simulate this from DFT calculations. Then I presented this work at the REC in 2018, and I had actually a picture from an old presentation. And actually, the first notes that I took at this conference was about these copper porphyrins. And I guess the most interesting one was this here. It's 2 copper porphyrins. They're fused together, and I think apparently, I'm not sure, but apparently on the poster it says that the J coupling of this is roughly 200 megahertz. This was a poster of Sabine Richert, who I think was just left Chris' group, if I remember correctly. So these copper porphyrins, they are synthesized in the group of Harry Anderson, and in this case it was Bart Limburg, and they had this single one, an affine fused one, singly linked, and then these fused ones. And here on the right, you can see some of the CW spectra. And basically, just Sabine, it was just difficult to simulate these spectra, basically. And so she asked Gunnar, well, could we actually just measure the hyperfine coupling directly, that we at least know this part, and then, we could maybe figure out the J coupling later. And I'll come back to this point a little later. And we just tried, or I tried a little bit before to actually see EDNMR lines of metal coupling. So read the hyperfine coupling to the copper, and then see, because you would expect that you could see the correlation to the G tensor, and this might give you some information. And this was quite funny because this was the EDNMR spectrum, and in red you can see the signal intensity without any hole burning pulse. And the funny thing about this, that you do a hole burning pulse and then you see enhancements, which is not really a hole. And in principle, you already saw the physical principle just like one talk before. Obviously, you can enhance transitions if you have, well, more than one level that are connected. So if you just have to spin 1/2 coupled to a nucleus, you can never get an enhancement in an EDNMR. But if you have an S equals 1 state, let's say the populations are distributed like this, and let's say you invert this transition here. You invert these 2 populations, and then this transition here is hyperpolarized, basically. So this is what you saw here. And this was used for signal enhancements before, but it was actually never used spectroscopically. So what you can do is that, okay, now we can take a spectrum, we can do this eDNMR spectrum at each point in the magnetic field sweep, basically. So this is a pseudo modulated, this was just an echo-detected field sweep here on top. And it looks like this. And I didn't really know what to do at the start, basically. I just want to highlight, this is actually pretty broad banded. So this is over more than 1.2 gigahertz. And I mean, you could say something from it. I mean, okay, in the middle, you would expect the central hole, and actually at 50 megahertz at Q band, you would expect the holes of the hydrogens. And there's definitely some coupled carbons, nitrogen 14, sorry. And then you have I mean, these ridges here, it was clear that they have to be related to the copper hyperfine, basically. And in blue here are actually the enhancements. So there's also some clear structure here. Now the problem was there was no way to simulate this. So I mean, you could. So EasySpin definitely couldn't do it at the start, and it was pretty unclear like how you even do this, because there's no chance that you do a full quantum mechanical calculation of the system. You know, if you want to do this eDNMR, probably you have to include relaxation, because otherwise you're like overflipping all the time, and it was kind of difficult. But there was a paper by Nick Cox where they did it, where they kind of used an algorithm that kind of took into account the forbidden transitions, but it only worked for spin 1/2. And so at some point, I actually managed to make it work for general spin system in EasySpin. And then I could start looking at a few possibilities. And one, I think, is actually a pretty nice example. You could actually simulate the echo-detected field sweep spectrum just with a rhombic G-tensor and no CFS. And if you look at the top here, this looks actually pretty, it fits pretty well. But the problem is, like, you know, is this a peak here at the end as well? And, you know, you don't quite know where to start. But in the 2D spectrum, it's clear this is just wrong. I mean, this is just clearly not the experimental spectrum. And what I did, okay, you could just assume, okay, maybe the G and A values are probably just the ones of the monomers. And if it's a spin in a spin 1 manifold, that the coupling is halved. And then I just took the zero field splitting of that you expect from the point dipole approximation, and that also doesn't fit. But then, I mean, when it fit, or if you just play around a little bit, actually it works very well if the G and A tensors are the same and in the monomer. But for some reason, CFS is just higher than you expect. I don't quite know what that means. There are definitely many more people here who know more about copper porphyrins or porphyries in general. So I guess that's on you to figure out why exactly this is the case. But the point was a bit, it's pretty clear that basically you have a spin 1. I could give, like, you know, a lower limit of the J coupling that makes sense, and clearly was much larger than they first expected. And then we did some squid, and so this kind of all worked out. But I just wanted to say what was really important here with these spectra is that you have to share your code. So when Nick Cox and Anton Savitsky, they published this paper where they showed an algorithm, and they posted it on the EasySpin forum, but it only worked for spin 1/2. And I just generalized it to general spin systems. But I think without this code, I would never have even started to doing it, basically. And that was pretty nice for me. I also made it available online. And then last year, actually, Kiran and Alice used this code for some water oxidizing complex, where they basically argued that some previously published spectra that were interpreted with Endor simulations might have been not really what the author thought. I don't know the chemical details in this, but I think it just nicely shows, like, if you share your code, you're really promoting some other people to do some more stuff as well. And then just, this is a nice story. So why were they not sure about the J coupling at all? So it's kind of common knowledge that if you have a very large J coupling in a dimer, that the effective hyperfine coupling is halved. And if you look at the CW spectrum, it's yeah, probably yes, this splitting here is roughly half. But they measured Endor, and probably they shouldn't have. Because when you look at this is just the same for the singly fused. Actually, it's also the same for the the monomer. Maybe I should have shown the monomer here. That would have made more sense. Here the J coupling is definitely lower. And so here you're like, no, it's clearly not half the hyperfine coupling. But it's just because we didn't really understand Endor that well. Because if you just simulate it, so if you take, it's just for nitrogen now instead of copper, but if you have a coupling to one nitrogen and you have another electron that is coupled to nitrogen, they have a slight G difference, I think. And then you change the J coupling in the CW, basically go from the two independent S equals 1/2 to a coupled spin 1 that couples to both spins the same way. You really see this change, but in the Endor of strongly coupled nuclei, there's actually no change at all up to this little bump, which is at the nuclear Zeeman frequency, but probably would never really detect this just because the hyperfine enhancement is like extremely low there, or at least we didn't see it. But yeah, this kind of settled the argument. You can also understand this from the energy levels if you think about it, but I won't. You don't have to. So now. That was kind of second project that I finished up, and I guess I had some stuff that I looked more into, but then some other duties came basically. But I first have to introduce a little bit. So this Gunnar in the 90s, he started with something that he called dressed spin resonance, and there's a reason why it's called dressed, but in the context of what we're doing, it just means spin locked. Basically, it has some other meanings in like quantum optics. And he did Endor hyperfine decoupling in Endor, basically. So he used a spin lock echo, and during this spin lock, he applied the RF pulse. And they did this so you could facilitate some assignments, basically. And they published this, and they had nice assignments here. And then there was this weird peak. He's at 35 megahertz, and then what it says is the peak designated with an asterisk is due to the excitation of electron spin transitions, and apparently that went through the reviews. Because like why should that show up here? Like why should you see a transition of, why should you excite the electron spins when you irradiate it with 35 megahertz? But Gunnar figured it out, and what actually and made a paper out of it. What happened? And all this peak is if you take your Endor resonator, your field is like this, and usually then the RF polarization is perpendicular to it. But you're never going, it's never perfect. There will always be a little bit off. And the problem is if the RF matches the nutation frequency of this spin lock, you're actually inducing a transition, and the transition moment of these transitions is due to the electron spin. So it's just 1,000 times more likely than for RF. So even if you have like sine of 1 degree, it still gives you enough that you can actually see it. So you can just take your Endor resonator and just actually turn it 90 degrees. And then what you see is really just a drop in intensity when you hit the nutation frequency. And if you change the microwave frequency, then basically you're changing the spectrum. I have to speed up a little bit. So why did I start on this work? Because it had absolutely nothing to do, maybe not nothing, but very little to do with what I did. So in summer of 2018, Gunnar, he planned to supervise Lucas on a project of distressed spin resonance. He kind of wanted to revive it a little bit. There was just one slight issue that at the same time, Gunnar became head of the department in chemistry at ETH. And it's a pretty big department, and it's kind of a lot of work. So the conclusion of this was basically that I was supervising this project. And I think I probably read the paper about it at the same time as a student. And I think I never properly worked with a Bruker Endor spectrometer before, so I was a little shaky at the start. Let's put it like this. But somehow Lucas still made something work. Okay, here's the malonic acid, the Schweiger sample, actually, again, as Stefan was saying. And I don't even want to kind of say what exactly you see here. It's like, let's say the spectrum was a little bit ugly, like, you know, whatever. This is what we have. But there was one interesting thing, that there was actually a peak at the proton Zeeman frequency, and that will actually come back later. Let's put it like this. And another, just because we did this spin lock echoes, there was just another thing that we saw that, I mean, other people knew all the time, but I realized that during spin locks, the relaxation is actually much slower than if you just have a free evolution. And it was just a random measurement, basically. That had nothing to do with the rest. So how does this actually work, the stress spin resonance? If you think about a normal pulse, you have a static field, Q band 35 megahertz, and then you irradiate with a wave, and basically there's omega 1. The microwave frequencies just has to match this omega 0, and then you get a pulse, and then you get a mutation basically of your spins. In the rotating frame, it looks something like this, that you're rotating around an axis, in this case, the x-axis. And let's say in our spectrometer, that was roughly 100 megahertz Rabi frequency. And now if you do a longitudinal modulation, this is a long set, and this is not affected by the rotating frame. So this is still a long set. And if you now match this modulation frequency basically to the nutation frequency of this pulse, it's basically the same picture that we started with. It's just tilted. But what I figured out then is that actually you don't even need a longitudinal field modulation, because you can also do it like this. It just has to be perpendicular to your spin lock axis. And if you think about it, if you have this and you just go a little back and forth with your effective fields, that's pretty much just a phase modulation. So, but it's a sinusoidal phase modulation. So you, instead of having an X pulse, you change it slightly to Y and minus Y, and you do this with a frequency that matches the nutation frequency around this pulse. And with an AWG, you can just program this. And Andreen never foresaw this, but it was actually really straightforward to do on this spectrometer. And then you get a pulse kind of in the second rotating frame. And so these phase pulses, they act on rest spins like pulses act on the normal spin. And so this is the kind of stuff I'm living for. So I know that at this point it's like, oh, what can you use for? But I just love it. So yeah. And there was another important idea then that came to the next project. And so during my NMR courses with Matthias and Beat Meyer, they once talked about this paper by Heinz and Waugh and Rim, which is called the violation of the spin temperature hypothesis. And what they basically did is they had an FID just in calcium fluoride, and they could get it back by using a spin lock for a certain amount of time. And the main thing that I took away from this is if you have a dipolar coupling, and you use a spin lock kind of in the effective frame, there's actually still a dipolar coupling left. It's just kind of twisted, and it's by a factor of -1/2. That's why you can kind of refocus it. So basically, they showed that you can reverse spin diffusion. This was basically the paper. That's why it was called violation of the spin temperature hypothesis. It's a fun fact. Apparently, it was first rejected because it violated the spin temperature hypothesis. Yeah, but the takeaway is here that if you have a homonuclear spin lock, which then you're not actually getting rid of the dipolar coupling, at least not completely. And then I basically just connected the ideas. Okay, you have slow relaxation. You're not getting rid of the dipolar coupling. Well, probably you can somehow figure out a way to do distance measurements with this. And I was pretty lucky because Agathe Varnas was in this case, I was at this point actually working on trityl distance measurements, which is nice because you can do the spin locking. And yeah, this compound was synthesized by Henrik Hinz in Adelheid Goth's group, which is extremely important, this collaboration. And I'm not going to tell you exactly how this experiment works, but basically you can do a spin lock, you can do some phase modulations in between, and you can kind of in this spin lock frame, you can do an echo. And if you do this, you actually see the dipolar coupling between the two trityls. And here, this worked beautiful way. And yeah, if you don't understand this now, don't worry. It has some limitations. So at longer distances, you get some artifacts in there. I think I know why, but I don't know how to solve it yet. We didn't really understand like this rotating frame relaxation, because there's a T1 row, a T2 row, and so on, and I'm not really sure what it actually means exactly. So this is something we have to get into a bit. And also, this will never work for nitroxides. You have to be able to spin lock the whole thing, and I don't think that will ever work for nitroxides. But if you could do it with tritils, might be that at some point we get much longer. What I think what's very nice about this project was, if I told you, yeah, I wanted to make longer distance measurements, and that's why I thought about it, and this was just not the case. Like, I mean, it literally started with me supervising a project that I had absolutely no idea about at the first. And this is really how it worked. And there were also so many bad ideas in between. But sometimes in the end, you still get a slightly better idea than before. And I think this is a beautiful thing. And also, which is very important, this boy is actually a very relaxed and very optimistic supervisor. I think he was always more optimistic that this would someday be something useful than me. I was just playing around, and he was like, yeah, this will. Yeah, and so lately I got into pulse DNP, and I would wish that I could tell you, like, I was working on a specific system, and I really wanted to boost the sensitivity and so on. But the reason I got to is literally this peak. So when you do the spin locks, and this is not an Endor peak, because the RF coil is longitudinal. It's not in the XY plane. So we were just, what the hell is this? And also, if you do it with nitroxide, this is Q-band now, and you do a strong frequency modulation or phase modulation, you also see this drop, and it's at the nuclear Zeeman frequency. And if you lose polarization on the electron, well, it's probably somehow related to polarization transfers to this nucleus. So Gunnar did some numerical exploration here, and he again proposed that maybe we could do like a master's project or something with this, and I have to speed up a little bit. So basically, we took an NMR spectrometer and we just attached it to a pulse CPR spectrometer, and it has some interfaces. And actually, this spectrometer was actually built by Daniel, so thanks again. And Renee helped him, and then Laura kind of used a low field NMR spectrometer attached to an EPR, and then you have a tuned NMR coil, and then basically you can just detect the nuclear polarization. So it's not not that difficult. And then you just do DNP a few thousand times and detect the proton polarization. So I can't go into detail that more, but let's say now we understand it. I would say actually we figured out a theory that is inspired by dipolar recoupling in solid state NMR. And basically you can see these resonance conditions here that you can easily calculate, and then scaling factors that give you this intensity. So the theory, I have to say here, it's just the position. So the overall enhancement is not predicted here. It's just the shape of these things. But I don't have the time to go in detail too much here, and I will spare you the theoretical treatment. Maybe one thing, there was one guy, the two guys helping me here. So Kong, he was in Bob Griffin's lab at the time, and actually we got in contact because he did also Zoom sessions, but in solid state NMR and DNP. This is how we got in contact again, and then we started talking about these modulated DNP, so on and so forth. He was actually also the first ever lab assistant that I had, but then it was about distillation. And Anders, he used to be a postdoc with Matthias, and he has a lot of NMR papers about dipolar recoupling. And he was actually the reason why I went to Aarhus now, because I want to figure out some more of these things. But let's just skip this. This is too much. Let's say just one more thing. I did DNP and X-band, and people are not super interested in 15 megahertz DNP. Let's put it like this. But what I thought, well, but we could use DNP as EPR people. And what I already showed this last year, so I'm not going into too much detail. But basically, you can do one DNP transfer, you can saturate your electrons, then you can do DNP again, and then detect it, basically. So you really could do a proper polarization transfer to protons and back. And the bottom line is here, it works. So basically, here this is for the so-called novel sequence. So if you radiate the electrons with the nutation frequency, it corresponds to the nuclear Zeeman frequency. You get very efficient DNP, and that's why you see this kind of peak here. And the cool thing about this is that, well, if you just wait after the DNP and then before you do the reverse transfer, you get the polarization longer than the electron T1 because you stored the polarization on the nuclei like properly and not just in a hole in the EPR line. And actually, if you deuterate the solvent, it's even crazier. So even after 100 milliseconds at 50 Kelvin with this tritrile, you still have like 90% polarization left. And the reason why I'm so excited about this is that, well, this gives you time to do things with the nuclei. So at this point, when I was in my PhD, the AWG didn't have indoor capabilities yet, but you can easily imagine that you have this scheme, you polarize the nuclei, and then you do something with the nuclei, then you bring it back. Like, I mean, this is an indoor experiment, but the difference is that you're not limited by the electron T1 during this time, which you are usually in indoor. And this is basically the next thing that I'm going to try to do to show that this hopefully also works. Well, with this, I also just want to thank everyone I kind of highlighted in this talk already. Also, the whole EPR at ETH group. It was a really, really nice time. Then I just want to highlight something. You know, it's actually very easy to start these theories. The hard part is keeping it going. And I really want to thank Thomas and all the guys here that kind of keep that going. And I hope that it will prevail. I'm just showing what I'm doing in my postdoc now. So I'm in Aarhus. I'm trying to assemble a spectrometer. It's a little further than now here. I forgot to take a picture when I left. I hope I'll have an echo in the next 1 or 2 months. And it's really trying to get them to this interface of EPR and NMR and DNP, because, you know, NMR people, they have a lot of tricks up their sleeves, but EPR is just really hard. So, and I hope that we can bridge this gap there a little bit. And so Niels Christian was actually super excited. So he actually funded to get a pulse EPR spectrometer, and I think we're going to get somewhere here. And with this, thank you, Ola.